So, let us start our first topic, that is the radiation heat transfer. It is your 21st class on the transport phenomena, in which we will study the radiation heat transfer. Radiation heat transfer. This is your first class on the radiation heat transfer. So, I am abbreviating it radiation heat transfer 1. So, let us come to the various aspects of radiation heat transfer one by one. As per the previous class, radiation is defined as energy transfer due to temperature difference by mechanism of photon emission or emission of electromagnetic waves. Emission of electromagnetic waves. No medium is required for such a mode of energy transfer. Such a mode of energy transfer or you can say no medium is required for propagation of electromagnetic waves. For propagation of electromagnetic waves, this implies such mode of heat flow requires vacuum. Requires vacuum. This is the transfer. This is the definition of the radiation heat transfer. Now come to the characteristic of radiation. The second important thing is characteristic of radiation. Characteristic of radiation. This characteristics of radiation is a function of wavelength. Characteristics of radiation is a function of wavelength. That is a function of lambda. In a tabular form, you can easily see that how this wavelength of variation gives rise to definition of different kinds of radiation. Type of radiation. If the wavelength is greater than 10 to the power minus 1 and it is less than 10 to the power 2, then this is called the visible radiation or ultraviolet radiation. Visible radiation it is called the visible radiation, or you can say thermal radiation also falls in this category, the thermal radiation. If lambda is greater than 10 to the power 2, this is called microwave radiation. This is called microwave radiation. if the lambda is greater than 10 to the power minus 1, but it is it is greater than 10 to the power minus 2 and it is lesser than 10 to the power minus 1, then this is called ultraviolet radiation. It is called ultraviolet radiation. And if lambda is greater than 10 to the power minus 4, but if it is lesser than 10 to the power minus 2, then these such radiations are called X-rays. In all these cases, lambda is measured in the micrometer. Please keep in mind that here in this classification, the value of lambda needs to be expressed in terms of micrometer. Now come to the Stefan-Boltzmann law. Come to the Stefan-Boltzmann law. Stefan-Boltzmann law. Mathematically, this law can be expressed as this law can be expressed as that the emissive power of an ideal surface E B, that is equal to sigma, that is the Stefan-Boltzmann constant, into temperature on the absolute scale raised to the power 4. This E B, it is called the emissive power emitted from an ideal surface per unit area. This is called your emissive power. This sigma, this is called the Stefan-Boltzmann constant. Stefan-Boltzmann constant. As I have said in the previous class, this is a term which can be derived from the existing principles of quantum mechanics and the statistical mechanics, and the value of this Stefan-Boltzmann constant is 5.67 into 10 raised to the power minus 4, sorry, 6.10 to the power minus 8 watt per meter square K raised to the power 4, that is Kelvin raised to the power 4. PABS, this is called temperature on absolute scale, that is the Kelvin scale, absolute scale, that is measured in Kelvin. If you examine the equation number 1, you can easily see that, as I have shown you in the previous class, that the quantity of heat energy transferred per unit time always contains a term that is called the heat flux term. The description of this heat flux will be further get cleared in the coming classes on the conductive heat transfer, once the radiation heat transfer is completed. But for every heat transfer to take place, the equation pertaining to that heat transfer must contain a heat flux term. But here you can easily see in the, as per the equation number 1, that there is no heat flux term, rather the emissive power term is there. The question arises, if this is representing the energy transmission from one place to other in a system, then there must be a heat flux term, but there is no heat flux term. So, that is the possibility that there must be some existing relationship which may be there between the emissive power and the heat flux term. In order to establish this statement, so if you are observing the equation number 1 doesn't contain any heat flux term. Rather the emissive power is there. Rather the term emissive power is there. It means these two terms are interrelated with each other. Are interrelated with each other. In order to have an understanding of the relationship existing between these two terms, let us take an example. Let us take example of two surfaces. One surface is at temperature T1 and the other at T2. Both the surfaces are infinite in dimension. Both the surfaces are infinite in dimension. And facing each other. And also let us suppose T1 and T2 they are greater than absolute 0. That means none of the temperature is equal to the absolute 0. So, since T1 and T2 is greater than absolute 0, it means both the surface will radiate energy, both the surfaces will radiate heat energy as per Stefan-Boltzmann law. So, the net heat flux. That means the heat flux released by the surface 1 minus the heat flux released by the surface 2. So, the net heat flux is equal to Q, that should be equal to EB1 minus EB2, that should be equal to sigma T1 raised to the power 4 minus T2 raised to the power 4. Here, by visualizing the equation number 2, it can be easily seen that the emitting power is a term which stands responsible as a replacement of the heat flux so far as the radiative heat transfers are concerned. So, by doing so, we can establish a relationship, we can visualize a relationship, we can visualize a similarity between this heat flux and the emissive power. Next is the Planck's law. Next is the Planck's law of radiation. Next is the Planck's law of radiation. In this law, emission of heat energy is expressed as a function of specific wavelength, lambda. Alternately, this is a relationship based on the wavelength and monochromatic emissive power. As the law is emissive power for a particular wavelength lambda, Eb lambda, that is equal to a function of lambda, where this quantity Eb lambda is called the monochromatic emissive power. It is called the monochromatic emissive power. If you study the graph between the Eb lambda and the wavelength lambda, will find a graph of this nature, as I am going to show you. This is the x-axis along which I am putting the value of lambda in the micrometer, and here along the y-axis this is the monochromatic emissive power Eb lambda. The unit is watt per meter square. You will find a curve of this nature. This. Now, taking the reference of this shaded portion, this is the nature of the curve drawn between the monochromatic emissive power as a function of wavelength measured in the micrometer. So, area of the shaded curve from the normal principles of integral calculus, it can be assumed that EB lambda, that is area of the shaded curve, that is equal to EB, that may be given as integration of y dx, that is integration of EB lambda into lambda, sorry, EB d lambda, integration from 0 to infinity. This will be the expression for the area of the shaded curve, that is the integration y dx, that is EB lambda d lambda, integrated from 0 to infinity, as because of the fact that the curve becomes asymptotic in nature after this point. So, the value of lambda should be taken from 0 to infinity. So, this EB equal to 0 to infinity integration EB lambda d lambda. Also, let it be question number 3. Let it be question number 3. Equation number 3 can be differentiated as, if you differentiate this equation number 3, because integration is a reverse process of differentiation. So, this dBE by d lambda, that should be equal to EB lambda. Let it be question number 4. This equation is a relation between the total emission power, that is EB, and EB lambda, that is the monochromatic emissive power. By using the principles of quantum mechanics, Planck's law may be expressed as EB lambda is equal to C1 divided by lambda raised to the power 5 into exponential C2 by lambda t minus 1. With reference to equation number 5, in equation number 5, C1 and C2 are given as C1 is equal to 2 pi C naught square into h. H is the Planck's constant here, 2 pi C naught square h, and C2 is equal to h C naught by k. Here k is the wave number, which gives the idea about the group and phase velocity of all the wave traveling through the three-dimensional space. So, C2 is equal to h C naught by k. The numerical value of this C2 is equal to 1.44 into 10 raised to the power 4 micrometer Kelvin. that is value of C2 equal to 1.44 into 10 raised to power 4 micrometer Kelvin. All these parameters H, C naught and K are this K. This is your small k, this is your capital K. Keep in mind, this is your small k, this is your capital K, this is small k here. H, C naught and K are quantum mechanical terms. This is all about the Planck's law. The next thing that we are going to study in the present class, that the derivation of this Stefan-Boltzmann law of radiation from the Planck law. So, the derivation, this is very important for you people, derivation of Stefan-Boltzmann law from Planck's law of radiation. The existing equation that is available with us, that is the equation number 3, that is the EB, that is equal to integration 0 to infinity EB lambda d lambda, and another equation that is available is us with a EB lambda equal to C1 divided by lambda raised to the power 5 exponential C2 by lambda t minus 1. With the help of these two equations, let us try to derive this Stefan-Boltzmann law of radiation. So, this will be our equation number 3, this will be our equation number 5. With reference to the previous written things, 3 and 5. Now, putting the values for C1 and C2 in equation number 5. We get EB lambda equal to C1, that is equal to 2 pi C naught square into H divided by, this is lambda 5 into exponential C2 is equal to H C naught by K into this lambda into T minus 1 raised to the power minus 1. Now, let HC0 by lambda KT is equal to x. This is the substitution that we have made in order to solve this integration once you put the EB lambda in this equation number 3. So, let us HC naught by lambda KT is equal to x. So, lambda is equal to HC naught by x KT implies that the value of d lambda is equal to h c naught by k into t into minus 1 upon x square dx. Now, taking the limit here, if lambda is 0 here, if lambda is equal to 0, then what should be the value of x? That is equal to x equal to infinity. And if lambda is equal to infinity, it means x equal to 0. That means if I am go through the transformation in the integrand available in this equation number 3 by the help of equation number 5. So, the corresponding limit that should be written as E b, that should be equal to integration 0 to infinity. Value of E b lambda is this 2 pi c naught square h by lambda 5 exponential h c naught by k lambda t minus 1 raised to the power minus 1 into d lambda. That means this equation needs to be transformed in terms of x. So, that equation can be further written as integration from infinity to 0, or better to transform first. That should be equal to integration 0 to infinity into 2 pi c naught square into h, and the value of lambda is h c naught by x k t. So, raised to the power 5. So, that means h to the power 5 c naught raised to the power 5 into x to the power 5 k to the power 5 this into exponential this x minus 1 raised to the power minus 1. And what is the value of d lambda? Value of d lambda is 1 by x square dx, keeping the sign here. Now, this expression has been termed in terms of x. So, the corresponding to lambda is equal to 0, we have to put the limit x tends to infinity, and when lambda is equal to infinity, then x is equal to 0. So, the limit needs to be changed in this manner. So, minus this infinity to 0. So, the expression for E b can be rewritten as changing this minus sign into plus sign, the value again limit again changed from 0 to infinity, then the minus sign will get removed, then 2 pi c naught square h into x 5 k 5 t 5 divided by h raised to the power 5 c naught raised to the power 5 x square into dx divided by e to the power x minus 1. So, the necessary transformation which can be done here one mistake is there. So, d lambda value has been transformed into 1 minus s square, and the thing which have been left out is this into this also needs to be incorporated here, s into h c naught by k into t, that has been left out here. So, into h c naught divided by k into t, that can be written as 0 to infinity this will k get cancelled out, here you will get k4, this t will get cancelled out, so it will get t4, h this, so this will get obtained as h raised to the power 4, c naught square and this c naught, so this will give you the c naught cube. So, c naught square will be left out here, x square x5 that you left here x cube. So, that may be written as integration 0 to infinity 2 pi into x cube k4 t4 divided by h4 c naught square this h also will get cancelled out, h, this is h cube. So, let us write h cube c naught square into dx divided by e raised to the power x minus 1. Taking all the constants outside, 2 pi, this is constant, this is the quantum mechanical constant k4, take it outside, temperature is constant T4 divided by C naught is a constant into x cube is a constant, integration 0 to infinity x cube dx divided by ex minus 1. So, that may be written as 2 pi k4 t4 divided by c naught square h cube into I. Let it be integration I. Let it be question number 6. Now, from the principles of integral calculus, we know the value of this integral, this infinite integral x cube dx divided by e to the power x minus 1, that is equal to 6 summation 1 divided by n raised to the power 4, value of n from equal to 1 to infinity, and this will be, if you carry out the sum of this infinite series, this is pi 4 divided by 15. Thus, from equation number 6 and 7, from equations 6 and 7, the value of this EB, that is the total emissive power, that is equal to EB, that is equal to 2 pi k4 t4 divided by c naught h cube into pi 4 divided by 15, that is equal to 2 pi raised to the power 5 k raised to the power 4 divided by 15 c naught square into h cube into t raised to the power 4. Referring to the statistical mechanics, the expression for Stefan-Boltzmann constant is sigma, that is equal to 2 pi raised to the power 5 k raised to the power 4 divided by 15 C naught square h cube. Let it be equation number 9. So, from the equation number 8 and 9, finally, we will get the Stefan-Boltzmann law of radiation as from equations 8 and 9, final expression for Stefan-Boltzmann law is EB equal to sigma e raised to the power 4. This is your Stefan-Boltzmann law, or you can say EB is proportional to T to the power 4, or EB is proportional to T measured on the absolute scale raised to the power 4. This is all about the Stefan-Boltzmann law and its derivation on the basis of the Planck's law of radiation. In the next class, we will try to understand what are the different radiation properties of surfaces, and apart from that, we will go through the concept of an ideal black body, the characteristic of specular and diffuse radiations, and we will try to derive the Kirchhoff identity regarding the emission power of a black body. Thank you.